Hello everyone and welcome to Calc lesson number 65. This is going to be the first lesson of section 5.4 where we will look at exponential function differentiation. Over the last couple of classes, we've been focusing on the function f of x equals the natural log of x. We know that that function is increasing on its entire domain and therefore it has an inverse function, which we are going to focus on next. The domain of that inverse is the set of all real numbers, and the range is the set of positive real numbers. The inverse function of the natural logarithmic function, f of x equals the natural log of x, is called the natural exponential function and is denoted as e to the x. So you may have learned it as y equals e to the x if and only if x equals the natural log of y. The inverse relationship between the natural logarithmic function that we've been studying over the past few days and the natural exponential function can be summarized here as the natural log of e to the x is equal to x, and e to the natural log of x is equal to x. Before we jump into the exponential function differentiation, let's review some of the properties of the natural exponential function e to the x. So just like we said in the previous slides, the domain is all real numbers and the range is from 0 to infinity. The function is continuous, increasing, and one-to-one on its entire domain. The graph is concave up on its entire domain, and then the limit as x goes to negative infinity is equal to 0, and the limit as x goes to positive infinity is equal to infinity. So that's just showing you guys the end behavior as we're going towards infinity or negative infinity. Additionally, we just want to recall some of the operations with exponential functions. So hopefully you remember if you have e to the a times e to the b, you can actually add those two exponents. And if you have e to the a over e to the b, you can subtract those two exponents because you have the same base. So take a second, pause this if you need to jot any of these important properties or operations down in order to use them in the next couple of examples. One of the most intriguing and useful characteristics of the natural exponential function is that it is its own derivative. So you have your two definitions here that you want to make sure to write down. The first is that the derivative of e to the x is actually just e to the x. And then the second, using the chain rule, is that the derivative of e to the u, where u is some function of x, is just equal to e to the u du dx, or more commonly, e to the u times u prime. So make sure you write these down and you have them, and then we'll go ahead and do some examples. So for our first example, we just want to find the derivative of y equals e to the 2x minus 1. Because there's more than just x as our exponent, we want to go ahead and use the chain rule definition. The derivative of e to the u is e to the u times u prime. So we're going to go ahead and choose our entire exponent as our u. So that's going to be u equals 2x minus 1. So the derivative of u prime, is just equal to 2. So the derivative of y, we're going to denote as dy dx, is equal to e to the u, so we can leave this as e to the 2x minus 1 times u prime, which is just 2. So I'm going to just clean this up. Dy dx is just equal to 2e to the 2x minus 1. So for now, I'm going to go ahead writing out all of my steps, but as we practice, you might be able to do some or most of these in your head. Okay, number 2 looks similar, but a little bit more exciting. Here the function is y equals e to the negative 3 over x power. Again, because there is there's a little bit more than x, we want to use that definition for the derivative d dx of e to the u is just equal to e to the u times u prime. So in this case, we're going to choose our entire exponent as u, so u equals negative 3 over x. And really, in order to take that derivative, it's going to be a little bit easier to write it as negative 3x to the negative 1. So now when we go to find u prime, we can keep our negative 3. Remember, when we're taking the derivative, we're going to move our negative 1 in front and make this x to the 1 less power, which would be negative 2. So we can simplify our u prime to be a positive 3 over x squared. So don't forget your basic derivative rules, even when you're just doing this little chain rule piece. So taking the derivative of our function y equals e to the negative 3 over x, our derivative dy dx is equal to e to the u, so e to the negative 3 over x, times u prime, which is 3 over x squared. So we can write our final answer here, dy dx, as 3e to the negative 3 over x all over x squared. Now usually we ask you to change all exponents to positive, but for this section, negative exponents are going to be okay in most cases. In our third example, we want to find the derivative where our function is y equals x times e to the x. Because we're actually multiplying two different functions of x, in order to take this derivative, we have to bring back the product rule, which remember tells us our derivative is f times g prime plus g times f prime. So let's choose our first function f as x and our second function g as e to the x. Taking our derivative dy dx using the product rule, it's our first x times the derivative of our second. So the derivative of e to the x from the definition on the beginning slide is just e to the x, plus our second function, which is just e to the x, times the derivative of our first, and the derivative of x is just 1. So take a second and pause the video if you need to go back and see how this matches the first times the derivative of the second plus the second times the derivative of the first. To clean this up, we're just going to notice that we have an e to the x in both terms, so let's go ahead and factor that out. So we have dy dx, our derivative, is equal to e to the x times x plus 1. Okay, for our fourth example, we want to take the derivative of y equals e to the x minus e to the negative x all over 2. At first glance, this looks intimidating until I look more closely and realize that my denominator is just a 2, which is a constant that can be pulled out to the front. So before I do any differentiating, I'm going to rewrite my function as y equals 1/2 times e to the x minus e to the negative x. Now when I start taking my derivative, I can keep my 1/2 on the outside like a constant multiple. So taking the derivative dy dx, let's keep our 1/2 on the outside, and now we can handle each piece on its own. So the first piece I'm going to take the derivative of is e to the x, and the derivative of e to the x is just itself, e to the x. Then I'm going to subtract, and in order to take the derivative of e to the negative x, I need to use the chain rule, the fact that the derivative of e to the u is equal to e to the u times u prime. So in this case, I'm going to choose my exponent. My u will be equal to negative x. My u prime, my derivative, is just going to be equal to negative 1. So taking the derivative here, I have e to the u, so e to the negative x times u prime, or negative 1. Now I can go ahead and simplify, so this derivative becomes dy dx is equal to 1/2 e to the x minus a negative becomes plus e to the negative x. And in my final step, I'm just going to distribute my 1/2 so I can write my derivative dy dx is equal to 1/2 e to the x plus 1/2 e to the negative x. And again, negative exponents are going to be okay during this unit. For example number 5, we want to find the derivative of y equals e to the x over x. Because we now have a function of x in both our numerator and our denominator, in order to take this derivative, we'll have to bring back our quotient rule, which you may remember says if you have a function f over a function g, your derivative is equal to your denominator g times the derivative of your numerator minus your numerator f times the derivative of your denominator all over your denominator squared. So let's go ahead and get started so let's first identify, let's identify our numerator as our e to the x and our denominator as just x. So when we go to take our derivative, dy dx, this will be equal to our denominator, x, times the derivative of our numerator, and the derivative of e to the x is just e to the x, minus our numerator, which is just e to the x, times the derivative of our denominator, and the derivative of x is just 1, and that's going to be all over our denominator squared, which is just x squared. From here, not too much we can do. We can just simplify that numerator a little bit. So let's write our derivative, dy dx. And factoring out an e to the x in our numerator, we're left with x minus 1 all over x squared. So we're just bringing back some of those old rules that we had when we previously did differentiation and now applying them with differentiation of our exponential function. Just a few more here today. For example 6, we want to take the derivative of a function y equals x times e to the x minus e to the x. When we go to take this derivative, our first term, x times e to the x, is two functions of x being multiplied. So in order to take this individual derivative, we will have to use our product rule. And then we can differentiate our second term on its own. So let's start taking our derivative of y. We get dy dx is equal to take the derivative of x e to the x, remember our product rule is f times g prime plus g times f prime, the first times the derivative of the second, plus the second times the derivative of the first. So our first function is x times the derivative of e to the x is just e to the x, plus our second function is e to the x times our first function, or times the derivative of our first function, the derivative of x is just 1. So that takes care of our product rule. Then we're going to subtract the derivative of e to the x, and the derivative of e to the x is just e to the x. So we have x times e to the x plus 1 times e to the x minus e to the x, and hopefully you're realizing that these two terms are actually going to cancel each other out. So we are left with our derivative, dy dx, is just left as x times e to the x. Okay, example 7 is easily the most exciting problem we've seen so far today. Here we're taking the derivative of y equals the natural log of 1 plus e to the x over 1 minus e to the x. Now, everything we've already learned about taking the derivatives and natural logs is not going away, right? The product rule, the quotient rule, we need to keep up those skills. So hopefully when you see the natural log, you think, hey, I should maybe rewrite this before I do too much else. So let's first start by rewriting using the properties of logarithms. So let's write our function y equals, and because we have division, we can break up using subtraction. The natural log of 1 plus e to the x minus the natural log of 1 minus e to the x. Now our goal here is to take the derivative, so in order to do that, we need to recall that the derivative d dx of the natural log of u is equal to u prime over u, so from our last chapter. So we're going to do that twice. We're going to do it for our first term and our second term. So taking our derivative, dy dx, for our first term, the natural log of 1 plus e to the x, our u would be 1 plus e to the x, and then our u prime, the derivative of 1 would just be 0. The derivative of e to the x would be e to the x. So our u prime over u for our first term would be e to the x over 1 plus e to the x. And then we will subtract our second term. And for this term, we'll let our u be 1 minus e to the x, which makes u prime. The derivative of 1 is still 0. The derivative of negative e to the x is negative e to the x. So our u prime over u would be negative e to the x over 1 minus e to the x. And we can simplify just by combining our minus and negative. So our derivative, dy dx, is equal to e to the x over 1 plus e to the x plus e to the x over 1 minus e to the x. So no need to find a common denominator right yet, but just double checking your derivatives and then again bringing back this derivative of the natural log function. Okay, for our final example of the day, number 8, we want to find the derivative of y equals e to the 2x times tangent of 2x. Now, the first thing we want to notice is that because we are multiplying two functions of x, we are ultimately going to need to use our product rule, which remember tells us f times g prime plus g times f prime. Now when we go to take the derivative of each piece, when we take the derivative of e to the 2x, because we have more than x, we're going to need to bring in the definition d dx of e to the u is equal to e to the u times u prime. And when we go to take the derivative of tangent of 2x, because there's more than just an x inside our tangent function, we're going to have to use our chain rule. So lots of exciting things happening in here. So to start taking our derivative dy dx using our product rule, we want our first function, e to the 2x, times the derivative of our second function. And I'm actually going to label it as d dx of our second function. And our second function is that tangent of 2x plus our second function, which is tangent of 2x, times the derivative d dx of our first function e to the 2x. So I've written out the product rule, but I've identified the two pieces I still have to actually handle are those two derivatives. So when we go to take the derivative of tangent of 2x, we're going to be using the chain rule. So the derivative of tangent is secant squared. So we're going to take the derivative of our outside function and then multiply by the derivative of our inside function. So the derivative of tangent is secant squared. We keep our inside the same. Then we multiply by the derivative of the inside. And the derivative of 2x is just 2. And then, of course, we still have the rest of this. dy dx equals, plus, then we still have our tangent of 2x, and when we go to take the derivative of e to the 2x, our u would be 2x, and our u prime would just be 2, so this would be equal to e to the 2x times 2. And from here, we can just go ahead and simplify whatever we can. So we have dy dx is equal to, I'm going to write this as 2 e to the 2x times secant squared of 2x plus 2 e to the 2x times tangent of 2x. And you might have noticed that we wrote this 2 e to the 2x twice, so let's just factor that out to the front. So our dy dx is equal to 2e to the 2x times secant squared of 2x plus, oh rats, hold on, let me find some more room. Okay, our dy dx is equal to 2e to the 2x times secant squared of 2x plus tangent of 2x squeezed in there. So again, a lot happening. We had to first use our product rule, then we had to use the chain rule for our tangent of 2x, and then our new rule for e to the u. So pause the video. Sorry if you can't read this. Ask your teacher if you have any questions. Okay, great job with these new differentiation rules. Homework 65 is on page 352, numbers 33 through 51 odd, and as always, reach out to your teacher if you have any questions.